Hello and welcome to the third tutorial on JewelryCAM. In this lesson we'll begin discussing custom operations and how they can be used to cut any arbitrary geometry, such as this ring. It's a very simple example, but it will serve a purpose as well. You'll see we have a ring here with some engraving on the inside as well as a support. So to begin, we'll go to Custom Operations, select Geometry, and select everything that we're planning to be milling. Press Enter. We get our stock preview. And once again, it's quite important to define your stock as accurately as possible to what you'll actually be using, as that will help our program to avoid collisions or rapid transfers within the wax block. And now we're presented with our operations list, which is blank. To begin, we click Add New Custom Operations. Here we get to select one of the 6 types of cutting patterns, and most likely you will be using the first 3 predominantly, followed by swarfing and very occasionally engraving. But let's begin with the simplest one called Cut and Curve. Cut and Curve is exactly what it sounds like. It's instructing the mill to move the bit along a certain curve. So first, we're asked to select the viewpoint, so we'll select the one from the top. Press Enter. Selecting the viewport allows you the program to determine the orientation of the curve as well. So here we're following the curve this way, so top viewport it is. We select our curve, press Enter, and you'll see that the operation has been added, although not calculated. We have some settings that we can specify. In certain cases it's useful to cut beyond the curve. For example, if your stock goes beyond this curve, you can specify that it goes out of these boundaries, and in our case it's not relevant. Depth of a cut, which means how much below this curve you want the cut to be, and the number of cuts to make. So for example, if we specify 1, you will see that it cuts just 1, whereas if we specify 3, it will cut all 3. So let me demonstrate that to you. So we'll click Calculate, and here's our 1 cut, a slightly greenish line. And if now we simply change it to 2 and recalculate, you will see that JewelryCAM produces 2 cuts 1 millimeter apart. There we go, which can be useful at times too. Finally, there's another useful feature somewhat hidden in the setting, and that's the mirrored operation. We click it once and you'll see that a mirrored operation has been added below. You can recalculate it and you'll see that produces the same effect, but just mirrored over our axis here. So what's the purpose of this cut? Well, most often it's to remove excess stock that we do not need. So if your wax stock is square or rectangular, this will trim it down a little bit to perhaps avoid working through a whole bunch of excess wax. I often use this to trim down some irregular block to something pretty closely resembling my model. The reason I didn't cut it this way with a deep curve is that I don't want to compromise the structure here. I want the support to hold on as long as possible so that there's less resonance and less chance of it breaking off during the milling operation. So that's in essence cut and curve. Very useful for engraving or cutting simple lines, trimming stock, that sort of thing, cutting out maybe the center of this ring, and so on and so forth. Let's look at another type of operation, namely parallel cuts. Parallel cuts allows you to cut in a one-directional way within a boundary specified by a closed curve. Once again, specify a viewport, press Enter, select a boundary curve or several. So let's select the inside and the outside of this ring, and a little bit of stock support material, and press enter. And you'll notice that we have different settings here. We have a step over size, which I'll leave at 0.03, orientation, toolpath starting point, tolerance, and a few others. To us, the most useful settings are step over size, which will define resolution. 0.03 will be plenty for this ring. Orientation of the toolpath, X or Y. X will cut moving the bit this way. Y will cut this way. It kind of depends on your preference, although there's a catch. If you're going to be cutting using the X direction, like so, you have to make sure that the toolpath starts here and ends here, so that you have the most support on this area. This is the general principle of milling, where you're always trying to mill from the furthest point of your support to the closest. If you're cutting using Y, using this movement, then it does not matter because you're applying equal pressure across the piece. So let me show you the difference here. Click Apply, click Calculate, and we're done. Now, if you zoom in, you'll see that these lines are going like this. Let's see it on our simulator. Now, remember, we have 3 operations here, several cuts on curve, and then 1 parallel cut. Click our simulator button. And once again, I'll set the stock to transparent and the workpiece to show, so that you can see our final piece embedded in here. And let's run a simulation. So here's our initial cut and curve. It's trimming off some edges, excess material, and here's our parallel cut. I will speed up the simulation a bit. And you can see that it's going in a Y direction, and even though we specified the boundary curves just slightly overlapping a ring, it's still cutting the inside. And the reason for that is because, of course, it has to move the bit to the next point. So when it, for example, when it finishes here, it has to go here, so it traverses here. And what that means is that we end up cutting out this entire area. This is both good and bad, depending on how you look at it. If you now do the opposite side, as we will do shortly, then really essentially your ring is complete. You don't need to cut out the center part because it's already been milled out. The downside, of course, is that it takes a little bit longer to mill because you have all of this space to cut. So we will see that there's an alternative that will only cut this area, leaving the inside part alone. Now, we've seen the Y cuts. Let's see the X cuts. So if we change our orientation to X and recalculate, you will now see that our cutting lines, toolpaths, are facing a different way. Let's just disable these for a sec and then have a look at the simulator. And you see it begins correctly at the point furthest away from the stock holder, moving slowly towards our chuck. This is good. This is the correct orientation and the good way of cutting using the X direction. If it started here and moved that way, we would have to reverse the toolpath, and we could do that by specifying or by checking this TP start as reverse once and clicking apply. In this case it works well, so we're happy with it and we will leave it. Now, one more thing that we can do, although in this case it's not really applicable, is that we can specify a boundary plane or boundary surface. So here you can see that we're cascading up to this point on the model, and if our toolpath was way out here, we would be cutting down potentially even lower, kind of waterfalling off this model quite a fair ways. In order to avoid that, we can add surfaces that we'll add as a block. So simple planar surface command in Rhino will do that. Let's say we create this big flat surface here, and you'll see at the current moment we're waterfalling beyond it. But let's say we want to always stop right at this point. What we do in our settings is click this last button, set additional check surfaces, and click on the surface and press enter. Now, when we recalculate, you will notice that the toolpaths will no longer go beyond this point. This is very useful when you have holes or other areas where you want the milling to stop. And these objects can be added, as you saw, after you've selected your initial geometry. The only condition is that you do not remove them before recalculating any further operations, or before you make any further changes to this operation. We can hide this one for the time being, and let's see what else we have here. We have our calculate toolpath option, change the view plane, change machining direction, and change the boundary curves. All of these buttons allow you to change the initial parameters that you specified when calculating this toolpath, so that you do not have to go to a new operations and redo certain steps. Now let's complete this by going to a different direction, this side, the opposite direction, and performing a similar operation. We do this by using standard C-plane commands in Rhino. Here I'm using the C-plane tab and switching back and forth between the C-planes until I find what I'm needing, and always using a top viewport as our kind of eye on the milling direction. We will add a new custom operation, parallel cuts. You'll see that it retains the orientation, and we will perform this calculation. So now, here's an interesting thing that happened. We have not specified any boundaries, any boundary surfaces, and it has waterfalled a ways down. The reason why this happened is because I only specified this outside boundary curve and not this inside curve. So we can correct that by going to our second operation, change boundary curve, selecting the two curves, and now recalculating a toolpath once again. So you see that we can either use surfaces or closed curves as a means to preventing excessive operations. And now you can see that our ring is fully covered by our two operations, with the exception of our engraving, which we will get to in a moment. But before we do, I wanted to show you another milling operation that may be preferable in some circumstances. This is good, and this is useful for times when you have ample opportunity to cut out your model and you are really not in a hurry to do your cuts. So the upside is that once these two operations are performed, your ring is essentially done. There's no inside component, the whole inner part is cut out, and everything looks good. The downside, of course, is that you spend some extra time cutting out this inside part, which you could save. So now let's look at a different way of cutting the same ring using a different strategy called drive surfaces. Drive surfaces are basically a different way of specifying boundaries which the mill should follow when cutting your ring. And the big difference is that while our curves, of course, are only two-dimensional, in the sense that they can only specify boundaries in 2D, our drive surfaces can be 3 dimensions, not just specifying an area but also an angle. But of course they can also be 2D as well, and that in itself has some advantages. So let's begin with very simple 2D flat drive surfaces. So here's one, for example, that I've added. It's basically a silhouette of those two boundary curves made into a planar surface. So let's click Add New Custom Operation, specify Drive Surface, select this drive surface. You'll see it will ask us for direction of approach. We'll use this direction. Lead curve, we'll use the boundary edge for the lead curve, which will mean that it will cut things this way. And for boundary curves, we'll leave that be. We'll just use the drive surface itself. In the settings, there are a few familiar things and some new things. Step over size is the resolution that we've seen before. Depth below surface is the distance it's going to go down before it stops, even without any additional surfaces. We can specify reversing of the curve, lead curve, which will move our toolpath in a different direction, and a few other things such as re-specifying drive surface, boundary curves, and so on and so forth. Our default options will work quite well, and as you can see here, just turn off the drive surface. Here is our operation. That looks very similar to what we saw with boundary curves, but there is a key difference, and we will see it when we go into simulation. As you probably remember, using our boundary curves, we cut the entire piece, including inside. Here, you will notice it does something different. Instead of going across and cutting out this middle part, it will simply follow the outline of the geometry, or to be more precise, it will follow the outline of the drive surface, and it will only cut that, excluding anything outside or inside of it. So now what you see, especially if we set the stock to non-transparent, is that we have this inner part still remaining. We can perform a mirrored operation. We have to do this manually. For now, there's no option to automatically create a mirrored toolpath of this sort, so we'll just use Rhino tools to mirror our drive surface, switch to a different direction, meaning this perspective, and add a new operation. As you can see, even though it is a manual process to create this mirrored operation, it really doesn't take that much time. Fortunately, JewelryCAM retains all of our settings from the previous toolpath of a similar sort, and we calculate it, hide our drive surface just for the sake of clarity, and you'll see now we have our mirrored operation done. Once again, going to the simulator, we'll be able to see the difference, the key difference between using this and a parallel line strategy. I'm going to leave the stock as is and just speed up the simulation to show you exactly how things look when they cut. So you can see we kind of go around this sort of circle and then flip over to the other side and do the same thing. And as you imagine, at this point, it's quite likely that the centerpiece will fall out, especially if our drive surface extends a little bit beyond the geometry, so there's a bit of a gap. This is a slightly faster operation, or a faster way of cutting things than the other way, which will have processed the other central part. So here the estimate is about 1 hour at this resolution, whereas with the previous boundary curve it was about 1 hour and 47 minutes. So we save just about half the time. Now, to get full appreciation of the power of drive surfaces, we need to look at ones that do not lie strictly in a planar, flat way. So, for example, if we have a drive surface that looks more like this, curved inwards, we can do a nice cut involving all 5 axes while targeting the inner part of this ring. Let me show you how this is done. So this was created using a simple sweep and a line. As you can see, we go to our drive surface option again, specify our direction, our lead curve, and we'll leave all the other options at default. Now I increase the step over size a little bit, simply to accelerate this calculation, but you get the same idea either way. Let's see what we have. Here we see now that our path is going this way, and it doesn't look all that unusual, with the exception of the fact that we're actually seeing something very powerful here, the full 5 axes of work. To appreciate this, we need to see simulator in action. Set our options as usual, and let's see what it does. We see that now, as the ring is being cut out at the inner part, all 5 axes are engaged. This is pretty powerful because it allows us to keep certain areas always perpendicular and not have to cut at strange angles just to reach them. We end up with perhaps somewhat unusual looking patterns in wax, such as this, but as you note, that inner surface will be fully cut out at this point. And that's the real true power of these drive surfaces. As you may have noticed, it's best to keep these drive surfaces in a fairly simple way. This is a singular surface, it's not poly surface, and it's composed of a sweep without too many kinks or curves. You will get the best quality of cut this way because the mill has to do relatively fewer moves for every single line, and it will already be adjusting the B and the A axes. It does not really need to tilt the other axis any further, so this will give you a good cut. And incidentally, you will notice that this will allow you to cut your engraving on the inside quite nicely. Of course, you don't always want this level of or to go around the full ring just to cut one segment, so you can do a partial sweep just to cover this area, and you might have to go to the other side and cover it here. So let's see how this can be done. So here I create a smaller sweep using these 2 lines and a sweeping rail of the inside of the ring, and I'm going to mirror it because I will need it for the other side as well. So now we have this 2-part drive surface. From this perspective, we're going to choose this drive surface, this direction, lead curve of the surface edge going this way, and press enter for all the other options. Now, for convenience, we'll just hide this one. We'll flip the model over to make sure that we're pointing the right way. Here we are. And create another operation using drive surface. Point in the same, or in the proper direction. Select the lead curve and leave the other options as is. and we can hide this drive surface as well. Now you will see that our side here, the 18K, has been covered. Let's see what it looks like on the simulator. Here's our side A, and here's our side B. You will see that we were able to cut this little engraving without having to specify complex boundary curves, determine which angles of approach we need, etc., etc. We could have done it with parallel cuts as well, but it would have taken us considerably more time than simply creating a drive surface and letting the machine and the program figure out the rest. So, before we complete this lesson, I did want to show you this alternative way using the parallel curves, just so you have an idea of what that entails. So, let me show you how that can be done. To do the same operation using parallel cuts, first of all, we need to position our ring in a direction that's appropriate to our cutting. We cannot rely on drive surfaces to automatically figure this out. So, using our C-planes interface, we're going to use rotate C-plane command to position our ring to about 45 degrees of inclination. Here you go, you can see it in the top window. And you can also see that I've created some edge curves around this 18K just so we avoid excessive milling. We could have also just drawn a rough box or an arbitrary shape around it, but this will make it a little bit more precise. We go into our pattern selector, parallel cuts, and we'll leave all the options as they are default. And now we've done one side approach. We can go to the other side and perform the same rotate C-plane command at a 45 degree angle. So now we're kind of looking at the same letters but from the bottom. Select our boundary curves, go into parallel cuts, and recalculate. Right, so we'll look at our simulator. We will see how this cut is performed. Once again, we'll set our options and run our simulation. The key difference that you will notice now is that our axes are stationary except for the X and Y. And we have these two entryways, one from this side and one from the other, cutting out our 18K. This is a more traditional approach that those of you who work with 4 or 5 axis mills are probably used to. And it does work for certain options, but in some cases it's not quite as good as the drive surface, simply because you don't quite get the same smoothness of the cut as you do with the drive surface option. And that's because your mill is stationed at one angle rather than turning as it's doing the cuts. So this concludes the first video on the custom drive operations. We still have yet to cover swarfs as well as engraving. Thank you for watching.